What if the faintest whispers in the sky are not echoes of our own beginning, but scars from another universe brushing against ours? In the vast darkness, where galaxies drift like lanterns scattered across an endless ocean, scientists once believed the universe was self-contained, a single stage, born in a single act of creation. Yet the more carefully they listened, the more the cosmos seemed to hold a deeper story, one written in vibrations older than the stars. In 1980, Alan Guth proposed a startling idea that in the earliest instant after the Big Bang, the universe did not simply expand, it inflated. Faster than light, faster than comprehension. Space itself ballooned in a fraction of a second, smoothing chaos into order. But inflation carried with it an implication even stranger. If it could happen once, it could happen again and again. Each burst, a new bubble universe blooming within an endless cosmic froth, 2 decades earlier. In 1965, Arno Penzias and Robert Wilson had discovered the cosmic microwave background, the faint afterglow of the Big Bang itself. At first it seemed like static, a background hiss, but it was the oldest light in the universe, silent record of creation. Yet as satellites mapped it in exquisite detail, an anomaly appeared, a vast, inexplicable cold spot, as if something enormous had pressed against the fabric of our universe, leaving behind a bruise. Some scientists proposed it was a void, an absence of galaxies. Others whispered of something more radical, that this was a wound left by another universe colliding with ours. They had not set out to find other worlds beyond our cosmos. They had only sought clarity. But in the static and shadows, the universe seemed a murmur of neighbors unseen and of a reality far larger than we ever imagined. The cosmic microwave background is the oldest light in the universe, a pale afterglow born when the cosmos was just 380,000 years old. It carries within it a frozen map of the infant universe, a relic untouched by billions of years, preserved in wavelengths stretched by time itself. For cosmologists, it became a holy text, a sky-wide image of how everything began. And yet, like any text, it holds both clarity and contradiction. When the first detailed maps of this ancient light were produced, scientists expected nothing more than small fluctuations, gentle ripples marking the seeds of galaxies. The standard model of cosmology, the framework that had guided decades of discovery, predicted near-perfect statistical uniformity, a smooth canvas peppered with noise. At just the right scale, for the most part, this is what they found. But there was also something else, a vast region, tens of degrees across the sky, where the radiation dipped far below expectation. It was not a minor statistical anomaly, it was a wound carved into the heavens. They called it the cold spot. Its presence was profoundly unsettling. In a universe governed by randomness smoothed by inflation, the odds of such a structure forming naturally were vanishingly small. Some calculations suggested probabilities as low as 1 in several hundred. Others argued it was even less likely. If the cosmos was a dice game, the cold spot was a roll so improbable it called the fairness of the dice itself into question. The shock lay not only in the anomaly's existence, but in its persistence. As data from the Wilkinson microwave anisotropy probe was refined, and later sharpened by the European Space Agency's Planck satellite, the feature did not disappear. It held firm. Each new survey confirmed its haunting presence, resisting dismissal as mere noise. It was as though the universe itself was insisting on a secret, one carved across hundreds of millions of light-years. Some argued that the cold spot could be explained by a supervoid, a gargantuan absence of galaxies, that, by gravitational effects, could stretch and cool the photons passing through it. But even that explanation strained belief. Surveys of large-scale structure revealed vast empty regions. Yes, but none with the depth or density required to produce so sharp and so lasting a chill. The void hypothesis seemed to crumble under the weight of observation, and so scientists turned to darker possibilities. What if the cold spot was not a void at all, but a scar? A lingering mark left when our universe brushed against another bubble, colliding in the silent violence of cosmic inflation. The very suggestion struck like thunder. The Standard Model was never built to accommodate other universes. It describes our cosmos as a singular entity, governed by known laws, sealed off from outside interference. But the cold spot did not fit within those neat boundaries. If its origin lay in another universe, then our own reality was not self-contained. It was one bubble among many, fragile, vulnerable, and perhaps doomed to further collisions. The scale of this possibility was staggering. If universes collide, the consequences are not gentle. Entire regions of space-time could be warped, physics rewritten, the fabric of matter and energy obliterated or remade. The cold spot might then be more than a curiosity, could be the first evidence that our universe is not safe, that its laws are not eternal, that beyond the visible horizon lies not emptiness, but other realities pressing against ours. To the scientific community, this was both exhilarating and terrifying. For some, it promised evidence of the multiverse, a long-theorized but never observed extension of inflationary cosmology. For others, it threatened to destabilize decades of careful models. The shock was not only scientific, but philosophical. If the cold spot was indeed a scar from another universe, then our cosmos was no longer unique. It was one island in an infinite sea, its story inseparable from others. Every assumption about cosmic isolation, about the self-sufficiency of physical law, would need to be re-examined. The universe once thought vast enough to contain all of existence, be revealed as a mere fragment of something immeasurable, and there was a deeper fear, a shadow cast by this possibility. For if universes collide, then they are not eternal havens. They are fragile bubbles adrift in a storm, subject to forces far beyond comprehension. One collision in the distant past may have left a scar, but what of the future? What if another universe, expanding unseen beyond our horizon, were, even now, rushing toward us? The cold spot became more than a region of darkness in the sky. It became a mirror reflecting our uncertainty back upon us. In its silence lay a profound question. Is our reality truly safe? Or are we living within a cosmos forever vulnerable to encounters with worlds we cannot see? For scientists who had once hoped the CMB would provide neat closure, a final, satisfying confirmation of cosmology's grand equations, the cold spot was instead a doorway into greater mystery. The data did not destroy the Standard Model, but it strained its edges. The framework held, but the silence of the anomaly whispered of truths yet unspoken. Thus, the shock of the cold spot was not in what it explained, but in what it refused to explain. It stood as a reminder that the universe, for all its mathematical elegance, still holds secrets deep enough to break our understanding. And in the faint chill of that scar, humanity glimpsed for the first time the possibility that we are not alone, not merely in terms of life, but in terms of universes themselves. The cold spot was never supposed to endure. Anomalies, after all, are fragile things. They often dissolve under sharper instruments, fading as precision replaces imperfection. For many cosmologists, the expectation was simple. As the tools of observation grew stronger, the mystery would retreat. But when the cosmos is asked to give up its secrets, it does not always oblige. Sometimes it answers with silence, and sometimes it's with deeper riddles. The first attempt to unravel the cold spot came through the Wilkinson Microwave Anisotropy Probe, or WMAP, launched in 2001. For 9 years, it painted the microwave sky with an artist's patience, mapping the faint temperature variations with unprecedented clarity. These tiny fluctuations, mere millionths of a degree, were the seeds from which galaxies, clusters, cosmic filaments would later grow. As WMAP revealed its full map of the early universe, showed extraordinary agreement with the Standard Model. The statistical pattern of fluctuations matched the predictions of inflationary cosmology with breathtaking precision. But the cold spot remained. In the southern hemisphere of the sky, a great region still shone dimmer, colder, and stranger than expected. And there was more. Other anomalies emerged, subtle but persistent. One was the alignment of multipoles, a peculiar pattern that came to be known as the axis of evil. Instead of the fluctuations being randomly distributed, as theory demanded, certain large-scale features seemed to align across the heavens, as if the universe itself carried a preferred direction. To many, this was heresy. Inflation was supposed to erase such asymmetries, stretching space into near perfection. In the most ancient light, a faint structure whispered of something beyond the reach of current understanding. Then came the observation of hemispheric asymmetry. One half of the sky appeared to host stronger fluctuations than the other, a tilt that defied the assumption of cosmic isotropy. If the universe was supposed to look the same in every direction, why did one side seem ever so slightly more restless? By the time the Planck satellite was launched in 2009, scientists hoped to resolve these lingering questions. With instruments of exquisite sensitivity, Planck charted the microwave background in higher resolution than ever before. The result was a masterpiece, the sharpest portrait of the infant cosmos. And yet, rather than dissolving, the anomalies hardened. The cold spot persisted. The axis of evil remained. The hemispheric asymmetry endured. It was as though the universe was unwilling to conform, offering instead a quiet defiance to human expectation. The persistence of these features forced scientists to ask again whether they could be artifacts of measurement, statistical flukes, or products of contamination. Every possibility was examined. Foreground emissions from dust in the Milky Way, errors in the scanning process, misinterpretations of data, all were scrutinized with unforgiving rigor. But the anomalies remained resilient under the weight of skepticism. Attention turned once more to the cold spot itself. If it could not be dismissed as error, perhaps it had a natural explanation within the fabric of cosmic structure. One proposal was the existence of a supervoid, an immense underpopulated region of space, hundreds of millions of light-years across. As photons from the cosmic microwave background passed through such an emptiness, they would lose energy through gravitational effects, producing a faint cooling signature. For a time, the void hypothesis gained traction. Galaxy surveys were directed toward the coordinates of the cold spot, searching for evidence of such a barren expanse. And indeed, there were hints of underdensity, fewer galaxies than elsewhere, a hollow in the cosmic web. Yet as the data accumulated, doubt returned. The void, though large, was not nearly deep enough. Its gravitational influence could not fully account for the magnitude of the cold spot, even in its emptiness. The universe seemed too full to explain such an absence. The more carefully scientists examined the cold spot, the more resistant it became to closure. Each new dataset added detail, but not resolution, depth, but not certainty. The hypothesis of a single vast void gave way to speculation about more exotic explanations. Perhaps the cold spot was the product of topological defects, remnants of symmetry breaking in the early universe, scars left from cosmic strings or domain walls. Or perhaps it was evidence of something far stranger, the wake of another universe colliding with our own. The possibility was unnerving. If true, the cold spot was not simply a region of statistical curiosity. It was an artifact of interaction, the bruise of an ancient encounter. Cosmologists had long treated the universe as a sealed domain, a self-contained reality governed by its own laws. But the cold spot suggested that its boundaries might be porous. The cosmos itself might have been shaped by events outside its own horizon. Even so, scientific method demanded restraint. Extraordinary claims required extraordinary evidence. And so, the investigations continued, layer upon layer, instrument after instrument, survey upon survey. Yet no single answer could banish the uncertainty. The cold spot remained as it had, from the beginning, silent, inexplicable, immovable. This persistence carried with it a strange weight. For in science, mysteries often diminish with time, chipped away by data until only clarity remains. But here the opposite occurred. The more precisely the sky was mapped, the more deeply the anomaly took root. It was no longer a trivial imperfection. It had become a symbol, a reminder that even at the height of precision cosmology, the universe resists total comprehension. The cold spot, the axis of evil, the hemispheric asymmetry, each of these anomalies might, in isolation, be dismissed as statistical noise. But together, they formed a pattern of defiance, a chorus of irregularities that suggested the universe's earliest moments were stranger than theory had yet allowed. And so the mystery did not close. It widened. For every hypothesis proposed, counterarguments emerged. For every dataset analyzed, new questions unfolded. Was the cold spot truly a scar from a cosmic collision? Or was it the manifestation of unknown physics, something lurking in the very foundations of reality? The deeper scientists probed, the more fragile the boundary between certainty and speculation became, and in that fragility lay the essence of the mystery. For the cold spot was no longer just a region of the sky, it was a challenge, a quiet insistence that the universe still held secrets vast enough to humble even the sharpest instruments. And the boldest minds, in the silence of that ancient light, the cosmos offered not an answer, but an invitation to keep searching, to keep questioning, to accept that sometimes the deepest investigations do not close mysteries, but instead expand them. The deeper scientists gazed into the cold spot, the more their questions pointed outward, not toward galaxies or voids, but beyond the very edge of the observable universe. For if the anomaly could not be explained by ordinary structure, then perhaps it was the shadow of something far more profound. The idea was bold, unsettling, it's almost unthinkable, that the scar was the mark of another universe colliding with our own. This speculation did not rise from fantasy, but from the logic of inflation itself. In 1980, Alan Guth's theory of cosmic inflation had rescued cosmology from contradictions, explaining why the universe appeared so smooth, so flat, and so uniform on large scales. It proposed that in the first fraction of a second after the Big Bang, space expanded exponentially, swelling faster than the speed of light. What was once smaller than an atom became, in an instant, larger than the observable cosmos. But inflation carried with it an implication more radical than its creator first imagined. If inflation can happen once, why not again? Quantum fluctuations in the primordial field that drove inflation could cause different regions to inflate at different rates. While one bubble slowed and cooled into a universe like ours, inflation might continue elsewhere, spawning more bubbles, each sealed off by horizons of space-time. This was not a single universe at all, but an infinite process, eternal inflation, giving birth to countless cosmic domains. In this picture, our universe is not infinite. It is a bubble, floating in a frothing sea of inflating space, surrounded by others, each expanding at incomprehensible speed. And if bubbles form in the same vast sea, they can collide. What would such a collision mean? Physicists began to imagine the consequences. Two universes rushing outward, their boundaries smashing together at relativistic speeds. The energy released would not be like the impact of galaxies or stars, but of entire realities. The fabric of space-time itself would ripple and tear. Matter could be annihilated in flashes beyond measure. Even the laws of physics might be rewritten, as the properties of one universe bled into the other. The cold spot, in this light, became more than a statistical anomaly. It could be a bruise left by such an ancient collision, preserved in the microwave sky as a ghostly reminder of cosmic violence. If this was true, then the CMB was not only a record of our own birth, but a window into the wounds of a larger multiverse. The scale of such speculation was terrifying. The standard model of cosmology had treated the universe as all-encompassing, its laws eternal, its horizon the ultimate boundary of existence. But collisions between universes suggested otherwise. Our cosmos was not the totality of reality, but one arena among many. The multiverse was not philosophical abstraction, it was a physical battleground, where bubbles of space-time brushed, merged, or destroyed one another in silence beyond comprehension. For theorists, the implications were dizzying. Could the fine-tuned constants of our universe, the mass of the electron, the strength of gravity, the cosmological constant itself be relics of this history, imprinted during or after collisions? Could life exist at all without the fragile balance that such events had left behind? Perhaps, they speculated, the very fact of our existence was contingent on the survival of our bubble in a storm of others. And yet, there was also beauty in the horror. If universes collide, they also create. Some models suggest that the Big Bang itself may have been the product of such a collision. In certain versions of string theory, our universe is imagined as a three-dimensional membrane, a brain, floating. In higher dimensional space, when two brains crash together, the energy of the impact could ignite a new cosmos, a birth by collision, written into the fire of expansion. Such ideas blur the line between catastrophe and creation. What we call a beginning may, in truth, be the aftershock of a greater event, unseen but eternal. Our universe, in this vision, is not the first, nor will it be the last. It is one chapter in an endless dialogue of collisions and rebirths, of universes sparking universes in an infinite chain. The cold spot, if it is indeed such a scar, whispers of this cosmic drama. Its chill suggests that the multiverse is not an unreachable abstraction, but something that has already touched us. Its presence makes the unthinkable tangible, anchoring speculation and data. But with this possibility comes fear. If collisions happened before, could they happen again? If another universe is expanding toward ours, invisible beyond the cosmic horizon, would we have any warning? Some theorists argue that we would not. A bubble of lower energy vacuum, if it collided with ours, could rewrite the very structure of physics in an instant. The speed of such destruction would be the speed of light. There would be no sign, no escape, no survival. This is the specter of vacuum decay, the idea that our universe is not in its lowest possible energy state, but a metastable bubble, vulnerable to collapse. Should it collide with a deeper vacuum, reality as we know it would be swept away, its laws erased, its matter dissolved into a new order. The cold spot, seen through this lens, is not merely a scar of the past. It is a reminder of the fragility of the present. To contemplate such a possibility is to confront the scale of human smallness. For all our history, our civilizations, our stories, everything rests upon the assumption that the universe is stable, that its laws will endure tomorrow as they do today. But if universes collide, that assumption falters. Our cosmos is no fortress. It is a bubble, delicate and finite, drifting in a storm we cannot see. And yet, the mystery carries with it not only terror, but wonder. If collisions are real, then we are not alone in the deepest sense. Beyond our horizon, other universes may swell, collide, and spark into being, each with its own physics, its own galaxies, its own possibilities for life. The multiverse, once dismissed as philosophy, becomes a stage of endless creation, a sea where reality itself is plural and infinity is not abstract, physical. The escalation of the cold spot's mystery lies in this duality. It transforms the anomaly from an isolated imperfection into a cosmic question. Are we witnessing the trace of another universe? Is our cosmos part of a larger, restless expanse where collisions are inevitable and where beginnings and endings are the same? The silence of the sky offers no direct answer, but in the bruise of the cold spot, in the alignment of anomalies, in the persistence of patterns that theory cannot erase, lies the possibility that the multiverse is not only real, but already written into the scars of our own, and so the mystery deepens, not with resolution, but with expansion. The cold spot is no longer a statistical puzzle. It is a window into a cosmos that is both more fragile and more infinite than humanity ever dared to imagine. The universe is a vast silence, but within that silence, patterns whisper. The cold spot, the scars in the microwave sky, the anomalies that refuse to fade, they all beckon toward something greater, something hidden beyond the veil of the observable cosmos. To explain such mysteries, science must lean into its boldest ideas, theories that stretch imagination to its breaking point, At the heart of these speculations lies eternal inflation. The inflationary model, first proposed to explain the smoothness of our universe, was never meant to create others. But quantum mechanics, with its restless uncertainty, makes even the simplest fields tremble. In the inflationary epoch, such fluctuations meant that while one region of space stopped inflating and cooled into a universe like ours, flatted, new bubbles formed endlessly, sprouting from the ever-expanding fabric. This is eternal inflation, a process without end, generating universes without number. Each bubble may be sealed from its neighbors by horizons too vast to cross, yet their existence cannot be denied by theory alone. And if universes are bubbles, then the anomalies in our sky may be their fingerprints, left when one brushed against another. Within this vision, our cosmos is not alone, nor is it privileged. It is one domain in a vast multiverse, each pocket universe with its own constants, its own rules, its own stories written in alien mathematics. The question then deepens: what governs these countless worlds? Here string theory offers a possibility. In its mathematics, reality is built not of point particles, but of vibrating strings, tiny loops resonating at different frequencies. From their vibrations arise the particles, the forces, the very scaffolding of nature. Yet the theory does not describe one unique universe. Instead, it admits an immense landscape of solutions, perhaps 10 or more. Each corresponds to a possible cosmos with different laws, different strengths of gravity, different arrangements of dimensions. In this string theory landscape, the multiverse is not just possible, it is inevitable. Every bubble born from eternal inflation may realize a different version of these mathematical possibilities, each as real as our own. Some would collapse instantly, their physics hostile to structure. Others would expand, lifeless but stable. A few, perhaps, would give rise to stars, galaxies, and even beings that gaze into the sky and wonder as we do now, whether they are alone. Yet not all speculations are so gentle. Some whisper of catastrophe. Among them is the specter of false vacuum decay. According to quantum field theory, our universe may not occupy the lowest possible energy state. Instead, it may be trapped in a metastable condition, a false vacuum, seemingly permanent, but ultimately precarious. If this is true, then somewhere, someday, a fluctuation could cause the universe to tunnel into a deeper vacuum. The result would be a bubble of new reality, expanding at the speed of light, rewriting physics as it consumed everything in its path. At its boundary, atoms would dissolve, forces would be redefined, and even the fabric of space-time would obey new laws. For those within its reach, there would be no warning, no escape, no survival. To contemplate such a possibility is to recognize the fragility of existence, the thinness of the fabric upon which all life depends, the cold spot. Through this lens could be more than a bruise of contact. It might be a wound, a trace of such a vacuum bubble colliding with ours in the ancient past. That we survived to see it may mean the collision was partial, or that its effects lay only at the edges of our cosmic horizon. But the possibility remains, casting a shadow across the comfort of permanence. Other theories imagine collisions not of vacua, but of dimensions themselves. In M theory, an extension of string theory, our universe is not a lone entity, but a membrane, drifting in a higher dimensional space. These branes can move, stretch, and collide. When they do, their crashes are cataclysmic, releasing energies vast enough to ignite an entirely new cosmos. In this vision, the Big Bang was not the birth of all things, but the aftermath of such a collision. Our universe may carry within it the memory of branes that collided before, and the potential of collisions yet to come. This idea, radical though it seems, holds a strange elegance. For if universes are branes, then the cold spot might be the scar of a brush between our world and another, a reminder that we are adrift in dimensions invisible to our senses. And the Big Bang itself, once thought an absolute beginning, becomes instead a transition, one fireball in a chain of collisions, an eternal cycle of destruction and rebirth. Speculations such as these are not without controversy. Too many. They feel like dreams too distant to be science, untestable visions painted on the canvas of mathematics. Yet the cold spot anchors them. It is not a theory, but an observation carved into the oldest light in existence. Its stubborn presence forces theorists to ask questions they might otherwise dismiss. And in those questions, the multiverse steps from philosophy into physics. Still, the theories differ in tone. Eternal inflation offers abundance, a cosmos made vast beyond imagination, each bubble safe in its isolation, collisions rare but possible. String theory provides diversity, a landscape of universes, each with its own identity, each perhaps necessary to explain the fine-tuning of our own. False vacuum decay brings dread, the recognition that existence itself is not guaranteed, that reality may be erased without warning. In theory paints a cycle, collisions not as accidents, but as the engine of creation itself. Together, these speculations weave a tapestry both terrifying and beautiful. They suggest that our universe, for all its grandeur, is not absolute. It is contingent, born of processes that transcend its boundaries, vulnerable to forces beyond its horizon. Its laws, once thought eternal, may be only local. One version. Among countless possibilities for humanity, the emotional weight is profound. To live in a single universe is to believe in uniqueness, in permanence, in laws that hold without question. To live in a multiverse is to confront fragility and also possibility. If collisions have shaped our cosmos, then reality is larger than any one universe can contain. The cold spot, then, is not only a scar. It is an invitation to imagine existence not as singular, but as infinite, not as safe, but as endlessly unfolding. And perhaps in that vastness lies a strange kind of solace. For even if our bubble one day collides, even if our laws dissolve, and our matter vanishes, the multiverse endures. Creation does not end with us. It continues, endlessly, across horizons unseen. The cold spot rests in silence, etched into the oldest light of the cosmos, but science does not rest. To confront the possibility of colliding universes, cosmologists turn to their instruments, fragile machines of glass, metal, and mathematics, and ask them to listen to whispers written across billions of years. The search begins with the cosmic microwave background, the faint afterglow of the Big Bang. This light, stretched into microwaves by the expansion of the universe, is a fossil, older than any star, older even than the galaxies themselves. It carries the memory of creation, imprinted in fluctuations less than a millionth of a degree. If another universe brushed against our own, space-time itself once rippled with the violence of a collision, its scars might still be there, hidden. In the fine structure of this light, the Wilkinson Microwave Anisotropy Probe, launched in 2001, gave the first high-resolution maps of this ancient radiation. Its data confirmed much of what theory predicted, yet the cold spot remained, stubborn and unexplained. Then, in 2009, the Planck satellite took up the task. With detectors cooled to a fraction of a degree above absolute zero, Planck charted the microwave sky with exquisite precision, mapping it down to the smallest ripples. Again, the cold spot persisted. The anomaly was not an illusion, nor a flaw. In the instruments, it was real. But mapping alone could not answer the deeper question. If universes collide, they may leave not only cold scars in the CMB, but other signatures, circular patterns, distortions in polarization, traces of non-Gaussian statistics that betray a violent past. Teams of scientists sift through the data, searching for these fingerprints. The task is meticulous, and the answers remain elusive. Yet the very act of searching binds humanity's curiosity to the vastest of scales. As if fragile eyes on a small planet might read the story of infinity, beyond the microwave sky, another tool waits in silence. Gravitational waves, predicted. By Einstein, a century ago, they are ripples in the fabric of space-time born from the motion of massive bodies. In 2015, detectors on Earth recorded them for the first time as black holes spiraled into one another. These were whispers from billions of light-years away, faint tremors passing unnoticed through everything. But if universes collide, the violence would be on a scale no black hole could match. The fabric of space-time itself would tremble. Such primordial collisions leave behind a background of gravitational waves, a cosmic hum older than galaxies. Instruments like LIGO and Virgo listen for these signals, while future detectors, LISA in space, pulsar timing arrays stretched across the galaxy, may yet catch the deeper bass notes of creation. If such a hum exists, it would be the most direct evidence of worlds beyond our own, the music of universes colliding in silence. The search does not end with telescopes and detectors. In laboratories on Earth, physicists probe the vacuum itself, the Large Hadron Collider, smashing protons together at energies unseen since the first instance after the Big Bang, searches for cracks in the laws of physics. Could the Higgs field be unstable, hinting that our universe sits in a false vacuum, vulnerable to decay? Could extra dimensions reveal themselves, pointing toward the brains and collisions imagined by M-theory? Every particle collision, every shower of debris, recorded in underground caverns, is another attempt to pull back the veil on reality's foundations. Meanwhile, theorists push further still. In quantum cosmology, they try to reconcile the quantum world with gravity itself, constructing models where universes are born not from singularities, but from quantum processes in a larger reality. In holographic models, they imagine that our three-dimensional universe is a projection from a deeper, two-dimensional boundary, a cosmic hologram. In such frameworks, a collision might appear not as bubbles crashing in space, but as boundaries intersecting in a higher dimensional reality. These are not settled theories, but they are attempts to grasp the ungraspable, to give mathematics to the whispers the cold spot leaves behind. And while instruments on Earth listen to collisions of particles, instruments in space look deeper, into the cosmos. The James Webb Space Telescope, perched beyond the Moon's orbit, stares into the first billion years after the Big Bang. Its mirrors, polished to perfection, gather the faint light of the earliest galaxies. Though it does not see the CMB, it traces how structure formed in the young universe, whether voids and filaments align with anomalies in the microwave sky, whether there are hints of distortions that might suggest something more. Future projects promise to go further. The Simons Observatory, the CMBs for experiment, and missions still on the drawing board seek to map the polarization of the cosmic microwave background with unmatched sensitivity. Polarization carries clues about gravitational waves from the earliest moments, about inflation itself, and perhaps about collisions beyond our horizon. If bubbles once crashed together, the echoes may be faint, but they may still be there, waiting for instruments precise enough to hear them. This is the nature of science at its frontier, a convergence of tools and ideas, each limited, each fragile, but together forming a net cast across infinity. Satellites orbiting Earth, detectors buried beneath mountains, telescopes unfolding in space, and equations written in chalk all reach toward the same mystery. Are we alone in the vastness of universes, or have others touched us already, leaving their scars in the cold silence of the sky? There is beauty in the persistence of the search. For even as the cold spot defies explanation, its very refusal drives invention. It forces science to refine its instruments, to sharpen its theories, to expand its imagination beyond the horizon of a single cosmos. It transforms uncertainty into curiosity, and curiosity into the patient work of observation, and yet behind every calculation and every map lies the same haunting possibility. If collisions are real, then the universe is not a sealed chamber. It is porous, fragile, vulnerable. The cold spot may be the first evidence of this fragility, a reminder that the laws we take as eternal may be local, temporary, contingent. Our universe may be one bubble among many, its boundaries scarred by encounters we can barely comprehend. Science seeks proof, demands evidence written in data, in signals, in light and waves and particles. But philosophy lingers in the silence. If the cold spot is a scar of collision, then humanity already carries within its sky the memory of another world. If gravitational waves hum from ancient crashes, then our universe is part of a greater chorus, an orchestra of realities. If laboratory experiments reveal cracks in the vacuum, then our existence is not permanent, but precarious. Perched on the edge of deeper truths, the search continues, relentless, fragile, and profound. Satellites still map the afterglow. Detectors still listen for tremors in spacetime. Colliders still smash matter into fragments of ancient fire. Each tool, each theory, each observation is a candle lit against the darkness. A signal sent into silence, and the silence answers, not with certainty, but with invitation. To keep building, to keep searching, to accept that reality may be larger, stranger, and more infinite than the word universe can contain. Beneath the night sky, humanity stands as fragile witnesses. Our planet orbits in quiet circles, a speck of dust warmed by a modest star, all of it encased in a universe we once believed to be absolute. And yet, the evidence carved into the heavens suggests otherwise. We may live not in the whole of reality, but inside a bubble, a temporary chamber adrift in an inflating sea, surrounded by countless others. If that is true, then our sense of permanence is an illusion. The laws of physics we take as eternal may be parochial, confined to the boundaries of our bubble. The strength of gravity, the charge of the electron, the very constants that allow stars to shine and molecules to bond, all may be local rules. No more universal than the air of Earth is to the vacuum of space. Beyond our horizon, another bubble may exist where those rules differ, where light bends strangely, where matter as we know it cannot survive. This realization is both humbling and terrifying, for it means our existence is not guaranteed by cosmic necessity, but contingent upon circumstance. The emergence of life, of consciousness, history itself, all are byproducts of physics that might easily have been otherwise. Perhaps we live only because our bubble has, for now, remained stable. Untouched by the chaos beyond, the cold spot whispers of this fragility. If it is indeed a scar from a cosmic collision, then our universe is already brushed against another. We are not sealed. We are not isolated. The bubble that holds us is permeable. Its edge is vulnerable to forces older and greater than anything we can imagine. If collisions have happened before, they can happen again. If they do, no law of science or act of will can shield us too. Contemplate this is to feel the weight of insignificance. Civilizations rise and fall, building monuments to permanence. Yet all of it rests upon a fabric that may, at any moment, be rewritten. A collision between universes is not war as we understand it. It is annihilation and rebirth on a scale that renders history meaningless. The rules of chemistry, the possibility of stars, the concept of time itself, all could dissolve in an instant, replaced by laws alien to us, indifferent to our survival. And yet within this terror lies awe. For if universes collide, they also create. The violence that erases one reality may give birth to another. The Big Bang itself may have been such an event, a spark ignited by the crash of brains, or the merging of bubbles, or the decay of a higher vacuum into something new. What we call beginnings may be only transitions. One universe yielding to the next in an endless sequence. This vision reframes existence. We are not inhabitants of a single, eternal cosmos, but participants in an infinite dialogue. Collisions are not endings, but exchanges, as universes brush, shatter, and seed one another across eternity. Each birth of a cosmos is a note in a larger symphony, one that has no beginning and no end. Only change. The cold spot may be the first evidence of this dialogue, a faint echo written in the oldest light. If so, then humanity, in its youth, has already glimpsed the vast machinery of reality. We are fragile, yes, but we are also witnesses to infinity, capable of perceiving scars left by forces beyond comprehension. The fact that we can even ask these questions is itself a miracle, consciousness reflecting upon collisions of worlds. And so, the night sky transforms. It is no longer a dome of stars, finite and self-contained. It becomes a window into a greater expanse, one where universes themselves are transient. It's one where existence is more fragile and more infinite than the human mind can bear. This leaves us suspended between wonder and unease. Wonder, because reality is larger than we dreamed. Unease, because we are not its masters, but its passengers. Drifting inside a bubble whose fate we cannot control, but perhaps fragility is not futility. Perhaps the meaning of existence is not permanence, but participation to live, to perceive, to marvel, even for a moment, at the vastness of it all. If universes collide and rebirth is eternal, then our story, though brief, is part of a greater story that never ends. And so the cold spot lingers in the sky, silent and indifferent. Maybe a void or a scar or a message from beyond our cosmos. Whatever it is, it reminds us that the universe is not finished, that creation is still unfolding, that infinity is not an abstraction, but a process, written in scars across the sky. Beneath this realization, humanity is left with a choice: to turn away, retreating into the comfort of old certainties, or to stare upward with new eyes, accepting that the ground of reality may shift, that universes may rise and fall, but that wonder itself endures. For in the end, collisions are not merely destruction, they are beginnings. The birth of universes is the eternal dialogue of infinity.